All right, thanks for watching. And I was talking to blackpenredpen a little bit, and he was telling me I should do more problems where I suffer. So today, let's diagonalize a 4x4 matrix. More specifically, take the matrix 4, -9, 6, 12, 0, -1, 4, 6, 2, -11, 8, 16, -1, 3, 0, -1. And let's try to diagonalize this. So the first step is to find the eigenvalues. And the way I like to do it is lambda I minus a. You could do a minus lambda I, completely fine. And what you get is, well, do minus everything and put lambda on the diagonal. So lambda minus 4, 9, -6, -12. Then 0, lambda plus 1, -4, -6. -2, 11, lambda minus 8, and -16. And lastly, 1, -3, 0, lambda plus 1. And at this point, check that everything is correct, because if you make a mistake here, everything else will be wrong. So lambda minus, so -4, 9, -6, -12, 0, 1, -4, -6, -2, 11, -8, -16, 1, -3, 0, lambda plus 1. All right, so very good. And now let's move on. And the nice thing is what we would like to do. All right, and now what we would like to do, we would like to expand along a row and column, especially ones that have lots of zeros. So for instance, what you could do, you could expand along the first column. And then what you get is the following. So lambda minus 4. And again, Bomberman all that. And you get the term of lambda plus 1, -4, -6, 11, lambda minus 8, -16, -3, 0, lambda plus 1. And now I kind of regret doing that, because that would be quite long. And then -0, plus -2. And again, you take Bomberman, so determinant of 9, -6, -12, lambda plus 1, -4, -6, and then -3, 0, lambda plus 1. And lastly, so plus minus, so -1 times determinant of this thing, 9, -6, -12, lambda plus 1, -4, -6, and then 11, lambda minus 8, and then -16. All right, so we did this 4x4 determinant. Now we have to do a bunch of 3x3 determinants. So this one, for instance, we can expand along the last row. Okay. And then what we get, I know, I hope you have all night for this. So then we get lambda minus 4. And then, so plus minus plus, so -3, Bomberman, -4, -6, lambda minus 8, -16, and then plus 0, so that doesn't matter. And then, so plus minus plus, minus plus, so, and then plus lambda plus 1, plus 1 times that determinant. So lambda plus 1, -4, 11, lambda minus 8. And then, good thing there's double speed, am I right? And then -2, and again here, same thing, expanding along a lot of zeros. So for instance here, -3, 0, lambda plus 1. And we get -2, so plus minus plus. So -3 times determinant of this thing, -6, -12, -4, -6, and then plus 0, plus minus plus, minus plus. So plus lambda plus 1, and then again 9 -6, lambda plus 1, and then -4. And again, do not expect any miracle here. So this is just pure suffering, if you wish. And then last but not least, let's just expand it along this first row. So 9 -6, -12. And then what we get is plus 9 and blackpenredpen owes me. So plus, no, sorry, we had the -1 here. See, we still have this -1. So plus -1 times 9, and then determinant of -4 minus 6, lambda -8 minus 16. And then 9 minus -6, so plus 6. And then lambda plus 1 minus 6, 11 minus 16. And then minus 12. And then we get lambda plus 1 minus 4, 11, lambda minus 8. There is something quite meditative to this, I do have to say. But let me just double check. So yes, looks correct so far. Okay, and then you have to expand out all those determinants. Oh my God. Lambda minus 4. And then we get, let's see if that takes more than an hour. That would be interesting. So minus 3. So minus 4 times minus 16, that's 64. And then plus 6 times lambda minus 8. Okay. And then plus lambda plus 1. And then lambda plus 1 times lambda minus 8. And then plus 44. Also, I hope I recorded this. And then minus 2 times, okay, minus 3 times 36 minus 48. And then plus lambda plus 1, so minus 36 plus 6 times lambda plus 1. And then one last time with this, so it becomes, if you want, we can just expand it out. So minus 9 times 64 plus 6 times lambda minus 8. And then minus 6 times, so minus 16, lambda plus 1 plus 66. And then, let's see, so minus plus 12 times, so lambda plus 1 times lambda minus 8. Like this. Lambda minus 8 and then plus 44. Okay, whoosh. Okay, now we can move on. So that was page 1 out of 7, actually. And then now expand this out. 1 second. All right. And now, next step, let's expand this. So that is lambda minus 4. And then let's simplify this a little bit. So minus 3 times 64 minus 48, that is 16. So 6 lambda plus 16, and then plus lambda plus 1. This one you can do lambda squared minus 7 lambda minus 8 plus 44, and which you can simplify to lambda squared minus 7 lambda plus 36. And by the way, you have no idea how many tries this took. It took me maybe 3 hours to prepare because I made like 8 algebra mistakes. And then what we get, so minus 2, and then so 36 minus 48, that's minus 12 times minus 3, that is 36. And then plus lambda plus 1, so 6 lambda plus 6 minus 36, so minus 30. And then, oh my God, this is so long. So what we have, minus 9, okay, 6 lambda minus 48 plus 64, so plus 16, and then minus 6 times minus 16 lambda plus 50, and then also this gibberish, so plus 12 times lambda squared minus 7 lambda minus 8 plus 44, which becomes lambda squared minus 7 lambda plus 36. Oh my God, I don't know where I am anymore. Okay. All right, and then now let's expand out the stuff in brackets. So we get, again, I'm proud of you for watching this. This is not, you have better things to do, but still. I would say this is ASMR, black pen, red pen. Okay, minus 18 lambda, and then minus 3 times 16, so minus 48 plus lambda plus 1, and then lambda squared minus 7 lambda plus 36. Okay, so we have that, and then minus 2. So this you can expand out, so to become 6 lambda squared minus 30 lambda plus 6 lambda, so minus 24 lambda, and then minus 30 plus 36, that is plus 6. And then all this gibberish, so minus 54 lambda, minus 144, and plus 96 lambda, and then let me see, minus 300, and then plus, so 12 lambda squared, and then minus 84 lambda, and then plus, 1 second, where is I? Okay, minus plus 432. Again, kind of crazy, but I believe you can. No, not yet. We'll do the deleting soon. Okay, so now we're still at the eigenvalues, by the way. So we still have a bunch of stuff to do. So then we get lambda minus 4, and then you expand that out. So minus 18 lambda minus 48, and then plus lambda cubed minus 7 lambda squared plus 36 lambda plus lambda squared minus 7 lambda plus 36. And then again, minus 12 lambda squared plus 48 lambda minus 12 minus 54 lambda minus 144 plus 96 lambda minus 300 plus 12 lambda squared. This is Sparta. Minus 84 lambda plus 432. And I believe here we can simplify some stuff, because the nice thing is the 12 lambda squares cancels out, and then we can put, the 48 lambda minus 54 lambda, 96 lambda, 84 lambda together, and we can put minus 12, minus 144, minus 300, and 432 together. So what we get in the end is lambda minus 4 times, so again, we have this lonely lambda cubed, and putting this thing together, minus lambda squared plus lambda squared, we get minus 6 lambda squared, and then minus 18 lambda minus 7 lambda plus 36 lambda. That's lots of lambs. 11 lambda, and then minus 12, so 36 minus 48. And this, surprisingly, just simplifies to something easy, plus 6 lambda minus 24. And then we're almost done with the eigenvalue. So now just expand this out. Lambda to the 4th minus 6 lambda cubed plus 11 lambda squares minus 12 lambda minus 4 lambda cubed. So now that's to the minus 4 plus 24 lambda squared minus 44 lambda plus 48 plus 6 lambda minus 24. Okay, now what can we do? So this lambda 4th comes together, and then minus 6 lambda cubed minus 4 lambda cubed becomes minus 10 lambda cubed. So 11 lambda, 24 lambda squared. So I think that becomes 35 lambda squared. And then, let me see. So we have the 12 lambda come together, minus 44 lambda, 6 lambda, and then we get minus 50 lambda. And then lastly, just the lonely numbers, so 48 minus 24, so that's plus 24. Whew. So the characteristic polynomial, P of lambda, is lambda to the 4th minus 10 lambda cubed plus 35 lambda squared minus 50 lambda plus 24. And you want to set it equals 0. So now we're ready for step 2. Again, we're still on page 2. I still have all this stuff to cover. Now, how do we find roots here? Here it's easiest to use the rational roots theorem. So all it says is if there is a rational root, which we might not know, then what we have is that P divides the constant term 24 and Q divides the leading term, which is 1. Which gives us a bunch of choices. So Q equals divides 1, that means Q equals plus or minus 1. So for the roots, we have to guess plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 6, plus minus 8, plus minus 12, plus minus 24. Okay, so again, if I really wanted to suffer, I would do all of that, but I'm not in the mood. So let's do lambda equals 1, and let's hope for the best. Well, let's see. 1 minus 10 plus 35 minus 50 plus 24. Well, that is if you want minus 9 plus 15. Sorry, plus minus 15. That's what I said. Minus 15 plus 24, and bazinga, that gives you 0. And if you want, you can try out the other roots, but let's just do the normal way. Let's do long division now. So we have lambda to the 4th minus 10 lambda cubed plus 35 lambda squared minus 50 lambda plus 24. And let's divide that, again, American long division, by lambda minus 1. And let's see what we get. So for instance, we can multiply by lambda cubed to get lambda to the 4th minus lambda cubed to get minus 9 lambda cubed plus 35 lambda squared minus 50 lambda plus 24. And then we can multiply by minus 9 lambda squared. So then what we get, so this, minus 9 lambda squared times lambda minus 1, so minus 9 lambda cubed. Lambda cubed and then plus 9 lambda squared. Again, I'm so proud of you. So 26 lambda squared minus 50 lambda plus 24. And who's still watching? Woohoo! And then plus 26 lambda. So we get 26 lambda squared minus 26 lambda, and then minus 24 lambda plus 24. So you can just do minus 24. And then what we get is minus 24 lambda plus 24, and we get 0. Okay, so what this means is that lambda to the 4th minus 10 lambda cubed plus 35 lambda squared minus 50 lambda plus 24, that is lambda minus 1 times lambda cubed minus 9 lambda squared plus 26 lambda minus 24. And of course, you're like, oh, I found a faster way. I don't care, because the point here is to do it the routine way, not the fast way. So in fact, now let's look at this lambda cubed minus 9 lambda squared plus 26 lambda minus 24. Well, this is, again, a rational polynomial, with rational roots. So let's apply the rational roots theorem again, which says, again, that if you have a root of the form P over Q, then a P divides minus 24, Q divides 1. Again, that gives you Q is plus minus 1, and you get another package of roots. So plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 6, plus minus 8, plus minus 12, plus minus 24. So now let's try out, well, lambda equals 1. 1 minus 9 plus 26 minus 24, that is minus 8 plus 2, that's minus 6. That doesn't work. Lambda equals minus 1, that's minus 1 minus 9 minus 26 minus 24. Well, it's negative. It can't be 0. Okay, well, again, not all hope is lost. Let's do lambda equals to 8 minus 9 times 4 plus 26 times 2 minus 24. So that's 8 minus 36 plus 52 minus 24. And woo, that is 0, which means all we need to do, we need to take lambda cubed minus 9 lambda squared plus 26 lambda minus 24 and divide it by lambda minus 2. All right, so let's do lambda squared. Again, this is super meditative for me. So lambda cubed minus 2 lambda squared. That becomes minus 7 lambda squared plus 26 lambda minus 24. So let's do minus 7 lambda. And then we get minus 7 lambda squared and then plus 14 lambda. Okay, and then imagine your professor asks you that on an exam. Oh my God. So 12 lambda minus 24, and then I guess plus 12, and then you get 12 lambda minus 24, bazinga. So it gives you 0, which tells you that lambda, this gibberish, so lambda cubed minus 9 lambda squared plus 26 lambda minus 24, that is lambda minus 2 times lambda squared minus 7 lambda plus 12. Okay. Here's a nice wrong trick. 12, it's 3 times 4. So actually, the roots are 3 and 4. But I do that to piss blackpenredpen off. We have that. So, however, careful. Remember, that's not our polynomial. Our original one was here. So the original polynomial is lambda minus 1 times all the other things. So in other words, lambda to the 4th minus 10 lambda cubed plus 35 lambda squared minus 50 lambda plus 24. This is, again, lambda minus 1 times lambda minus 2 times lambda minus 3 times lambda minus 4. You set it equal to 0, and lo and behold, the eigenvalues are 1, 2, 3, 4. This is math posting at its finest. All this work for 1, 2, 3, 4. And by the way, you could have guessed that with that rational roots if you actually plugged in 1, 2, 3, 4. But as I said, this is like the systematic way when the roots are not as easy. Okay, that was page 3. Now let's do page 4. So step 3, because we found all the eigenvalues. And yes, you guessed it, for every eigenvalue, 1, 2, 3, 4, we need to find the eigenvector. So step 3. So I would like to remind you that lambda I minus a was just a matrix lambda minus 4, 9, minus 6, minus 12, 0, lambda plus 1, minus 4, minus 6, minus 2, 11, lambda minus 8, minus 16, 1 minus 3, 0, lambda plus 1. All right, so now for our first eigenvector, let's let lambda equals 1. And what we have to find, the null space of, again, 1 minus 4, which is minus 3, 0, 9, minus 6, minus 12, 0, again, 1 plus 1, which is 2, minus 4, minus 6, minus 2, 11, minus 7, minus 16, 1, minus 3, 0, 2. Let me check. So it's important here to check that your answer is correct, because otherwise you make mistakes. All right. And then what you do here, you divide by minus 3, because everything is divisible by 3. And then here you divide by 2. All right. And then what you get, this is the null space of 1, minus 3, 2, 4, 0, 1, minus 2, minus 3, minus 2, 11, minus 7, minus 16, and then 1, minus 3, 0, 2. And yeah, you expect something easy, but unfortunately, all those eigenspaces will be one-dimensional. So very annoying systems to solve. For instance, here we can multiply by 2, and here we can multiply by minus 1. And we get the null space of 1, minus 3, 2, 4, 0, 1, minus 2, minus 3. And then let's see, 0, 5, minus 3, minus 8. And then 0, 0, minus 3, 2. Oh, no, minus 2, 2, I believe. Yep. 2, 2. Okay, and then what we can do, we can multiply this by minus 5, and this becomes a null space of 1, minus 3, 2, 4, 0, 1, minus 2, minus 3, 0, 0, and then 7, 7, and then 0, 0, 2, 2. Okay, but then you can divide this by 7, you can divide this by 2, and then subtract everything, and you get the null space of 1, minus 3, 2, 4, 0, 1, minus 2, minus 3, 0, 0, 1, 1, 0, 0, 0, 0. And then what you do, you can again multiply this by 2 and multiply this by minus 2. And what you get is the null space of, again, 1, minus 3, 0, 2, and then 0, 1, 0, minus 1, 0, 0, 1, 1, and then 0, 0, 0, 0. And again, I'll multiply this by 3. And then you get the null space of 1, 0, 0, minus 1, 0, 1, 0, minus 1, 0, 0, 1, 1, 0, 0, 0, 0. In our reduced row echelon form, so you can solve this. So I think x minus t equals 0, y minus t equals 0, z plus t equals 0. So in particular, if you take the vector x, y, z, t, that's just, okay, x is t, y is t, z is minus t, t is t. So tt minus tt, and then t times 1, 1 minus 1, 1. Okay, so that is our first eigenvector, 1, 1 minus 1, 1. And now the same thing 3 more times. Again, I think this is like a Britney Spears concert or something. I guess I should say Taylor Swift in those days. So let's take lambda equals 2, null space of minus 2, 9, minus 6, minus 12, 0, 3, minus 4, minus 6. I should start a band, like the Euler Transcendentals. Okay, minus 2, 11, minus 6, minus 16, 1, minus 3, 0, 3. So here, again, what I did, I just plugged in lambda equals 2 here. See, we had this. I just plugged in lambda equals 2, and you get that. All right, and then what can we do here? So for instance, also, yeah, what did I do? Yeah, so I just rearranged this. So again, just by rearranging this, the null space of, again, we like ones on the top. So 1, minus 3, 0, 3, and then minus 2, 9, minus 6, minus 12. And then minus 2, 11, minus 6, minus 16, and then 0, 3, minus 4, minus 6. So now what we can do, we can multiply this by 2, and we can multiply this by 2, and we get null space of 1, minus 3, 0, 3, and then 0, 3, minus 6, minus 6, and then 0, 5, minus 6, minus 10, 0, 3, minus 4, minus 6. All right, and if you divide this by 3, you get null space of 1, minus 3, 0, 3, 0, 1, minus 2, minus 2. And I totally did not do this again. And we get 0, 1, 5, 0, 5, minus 6, minus 10, 0, 3, minus 4, minus 6. And again, you multiply this by minus 5, you multiply this by minus 3, and you get null space of 1 minus 3, 0, 3, and then 0, 1 minus 2, minus 2, and then 0, 0, 4, 0, 0, 0, 2, 0. And again, you divide by 4, you divide by 2, and you subtract this from this. The point is, and also you subtracted 1 here, and you get null space of 1 minus 3, 0, 3, and then 0, 1, 0, because you subtracted from 1 if you want, minus 2, and then 0, 0, 1, 0, 0, 0, 0, 0, and you multiply this by 3, and you get null space of, I believe, 1, 0, 0, minus 3, 0, 1, 0, minus 2, 0, 0, 1, 0, 0, 0, 0, 0. And then what does that tell you? X minus 3t equals 0, y minus 2t equals 0, and z equals 0. So xy zt becomes, again, 3t, 2t, no t for you, and then t. So in other words, t times the vector 3, 2, 0, 1. All right, so we found our second vector, halfway done. And now we need to find our last two vectors. So now let's do lambda equals 3. So in this case, it becomes a null space of minus 1, 9, minus 6, minus 12, 0, 4, minus 4, minus 6. I just want to go to bed. This is so long. Minus 2, minus 11, minus 5, minus 16, 1, minus 3, 0, 4. Okay, and then again, rearrange this. So it's a null space of 1, minus 3, 0, 4, minus 1, 9, minus 6, minus 12, and then minus 2, 11, minus 5, minus 16, and then 0, 4, minus 4, minus 6. And again, you can spielen damit. You can play around with this a bit. So times 1, times 2, divided by 2. And so much stuff going on at the same time. And you get null space of 1, minus 3, 0, 4, and then 0, 6, minus 6, minus 6. Let's ignore that. And then 0, 5, minus 5, minus 8. And I hope. Okay, for a second, I thought my mic was off, but yeah, no, it works. 0, 2, minus 2, minus 3. All right, and then you divide by 6, and you get the null space of 1, minus 3, 0, 4, 0, 1, minus 1, minus 1, 0, 5, minus 5, minus 8, and then 0, 2, minus 2, minus 3. And again, I totally blame blackpenredpen for this. He told me to do this. Okay, and then you do minus 5 and then minus 2. By the way, that was like a year ago you told me, but what I remember. So 1, minus 3, 0, 4, and then 0, 1, minus 1, minus 1, and then 0, 5, no, 0, 0, 0, minus 3, and then 0, 0, 0, minus 1. And again, all this, this becomes 0, 0, 0, 1. So basically, null space of 1 minus 3, 0, 4, 0, 1 minus 1 minus 1, 0, 0, 0, 1, 0, 0, 0, 0. And then you see this 1, you just distribute on the other one. So it becomes null space of 1, 0, or let's see, 1 minus 3, 0, 0, 0, 1 minus 1, 0, 0, 0, 0, 1, 0, 0, 0, 0. And then you multiply this by 3, and then you get the null space of 1, 0, minus 3, 0, 0, 1, minus 1, 0, 0, 0, 0, 1, 0, 0, 0, 0. So what that tells you now is that x minus 3z equals 0, y minus z equals 0, and t equals 0. So essentially x, y, z, t becomes ez3z, z, 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 senor, and 0, and it becomes z times 3, 1, 1, 0. All right, third eigenvector, and then one more. So one more page, and then we're done. So lambda equals, I think step 3, right? Okay. So lambda equals 4. So then it becomes a null space. Oh no, that one's horrible. So 0, 9, minus 6, minus 12. Oh no, oh no, oh no, 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 no. Okay, 5 minus 4, 6, minus 2, 11, minus 4, minus 16, 1, minus 3, 0, 5. Let me drink some water. Oh. So we divide by 3. Okay, so this becomes, and then we rewrite and we rearrange. So again, null space of 1, minus 3, 0, 5, and then minus 2, 11, minus 4, minus 16, 0. What was it? Where did it go? Oh yeah, okay, sorry. 0, 5, minus 4, minus 6, and then 0, 3, minus 2, minus 4. And then this you can multiply by 2. And we get 1 null space, again, null space 1, minus 3, 0, 5, and then 0, 3, minus 2, minus 4, and then 0, 5, minus 4, minus 6, 0, 3, minus 2, yeah, minus 2, minus 4. And then the nice thing is we can subtract the third row from the second row from the third row. So we get null space of 1, minus 3, 0, 5, and then 0, 3, minus 2, minus 4, 0, 5, minus 4, minus 6. And then, let me see, 0, 0, 0. Oh yeah, no, I didn't even realize, yeah, that this is the same row, 0, 0, 0, 0. I was like, it can't be. Okay, again, forgive me. It's like 10 p.m. on a Wednesday night. So, all right. And then this, I know, unfortunately, we have fractions. So times minus 5/3. And then what we get, it's null space of 1, minus 3, 0, 5, 0, 3, minus 2, minus 4, 0, 0, minus 2/3, and then 2/3, 0, 0, 0, 0. And again, multiply this by 3/2. Get this B1, or I guess if you want, divide by 2/3. Let's do that. So divide by minus 2/3. There we go. And so we get null space. So luckily, even though it looks like fractions, they disappear. So 1, minus 3, 0, 5, 0, 3, minus 2, minus 4, 0, 0, 1, minus 1, 0, 0, 0, 0. And again, multiply this by 2. And then we get null space of 1, minus 3, 0, 5, 0, 3, 0, minus 6. 0, 0, 1, minus 1, 0, 0, 0, 0. And then again, You could divide by 3, but here let's just add this to it. And so we get, right, and then we get null space of 1, 0, 0, minus 1. And now we can divide by 3, 0, 1, 0, minus 2, 0, 0, 1, minus 1, 0, 0, 0, 0. And then we get x minus t equals 0, y minus 2t equals 0, z minus t equals 0. So xy zt is just t, 2t or not 2t, and then t and t. And so t times 1, 2, 1, 1. All right, whoops. Now we found all the 4 eigenvalues and eigenvectors. So like we found all 4 amulets. So now I believe step 4, our grand conclusion. All right, what did we find? For lambda equals 1, we had, I can't even read that. Let's see. We had, where did it go? For lambda equals 1, oh, there it is. For lambda equals, we had 1, 1, minus 1, 1. Okay. For lambda equals 2, so let's fire water. We have 3, 2, 0, 1. Wind, lambda equals 3. We get 3, 1, 1, 0. And earth, we get 3, 1, 1, 2, 1, 1. All right, and then all we have to do is put that together. So in other words, D is just a matrix of eigenvalues. 1, 0, 0, 0, 2, 0, 0, 0, 3, 0, 0, 0, 0, 0, 4. And then P is just a matrix of eigenvectors. So 1, 1, minus 1, 1, 3, 2, 0, 1, 3, 1, 1, 0, 1, 2, 1, 1. And with that said, we then get A equals PDP inverse. Woohoo! So congratulations, you have survived the matrix extravaganza, let's just say. And I don't know, maybe I'll do that again. I'm not sure. But anyway, I hope you like this. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.